Download this code from codegive.com, link in the description below. OK, let's dive into adding new nodes to a linked list. I'll cover it thoroughly with explanations, code examples, in C++ for clarity and common usage, and break it down for different scenarios you might encounter. While I can't exactly make it a shorts format, I'll keep it concise and focused on the core concepts. What is a linked list? Quick refresher. A linked list is a linear data structure where elements, called nodes, are stored in a non-contiguous manner. Each node contains 1 data * the actual information you want to store, example an integer, a string, an object. 2 pointer / link * a reference to the next node in the sequence. This pointer allows you to traverse the list. The last node's pointer typically points to null, or nullptr in modern C++. Why linked lists? Dynamic size * linked lists can grow or shrink during runtime without needing to pre-allocate a fixed block of memory. Efficient insertion / deletion * inserting or deleting nodes in the middle of a linked list is generally faster than in an array, as it only requires updating pointers, not shifting elements. Code example, C++, basic node structure. Explanation ***. Struct node, this defines the blueprint for our node. **int data, holds the data we want to store. I've used int here for simplicity, but you can replace it with float, string, or any other data type, or even a custom object. *node * next, a pointer that holds the address of the next node object in the list. If this is the last node, next will be nullptr. * node, int value, data, value, next, nullptr, this is a constructor. It allows us to create new nodes easily, providing the data when we create the node. It initializes the data and sets the next pointer to nullptr by default. Adding a new node, common scenarios. Let's explore the different places we might want to add a node to a linked list. 1. Adding at the beginning, head. 2. Adding at the end, tail. 3. Adding in the middle, after a specific node. 1. Adding at the beginning, head. This is the simplest insertion. The new node becomes the first node in the list. Explanation *. 1. Void insert at beginning, node head ref, int new data. Node head ref, we pass a pointer to the head node. This is crucial because we want to modify the actual head pointer outside the function. If we just passed node *head, we would only be modifying a copy of the head pointer within the function, and the original head would remain unchanged. *int new data, the data for the new node. 2 node * new node equals new node, new data, creates a new node object using the new keyword. This dynamically allocates memory on the heap for the node. 3 new node - next equals * head ref, this is the core step. The next pointer of the new node is set to point to the current head of the list, what head was pointing to before the insertion. * head ref dereferences the head ref pointer to get the head pointer. 4 * head ref equals new node, the head pointer is now updated to point to the new node, making it the first node in the list. 2. Adding at the end, tail. To add at the end, you need to traverse the list until you reach the last node, the one whose next pointer is nullptr. Then, you update the next pointer of that last node to point to the new node. Explanation * 1. If head ref equals nullptr, handles the case where the list is initially empty. If it's empty, the new node becomes both the head and the tail of the list. 2 node * current equals * head ref, we start at the beginning of the list, head. 3 while current - next equals nullptr, This loop iterates through the list until current points to the last node, the one whose next pointer is nullptr. For current dash next equals new node, the next pointer of the last node is updated to point to the newly created node, adding it to the end of the list. 3. Adding in the middle, after a specific node. To add a node in the middle, you need to find the node after which you want to insert the new node. Explanation asterisk. 1 if previous node equals nullptr, error handling. You can't insert after a non-existent node. 2 new node dash next equals previous node dash next, the next pointer of the new node is set to point to the node that the previous node was originally pointing to. This effectively inserts the new node into the middle of the list. 3 previous node dash next equals new node, the next pointer of the previous node is updated to point to the new node. Important considerations: memory management. Asterisk new and delete, or smart pointers in C++, when you use new to allocate memory for a node, you must use delete to free that memory when you're finished with the node. Otherwise, you'll have a memory leak. Asterisk destructor asterisk for more complex data structures, you should define a destructor for your linked list class to properly deallocate all the nodes when the list is no longer needed. Asterisk smart pointers, recommended modern C++ strongly encourages the use of smart pointers, example std unique _ptr, std shared _ptr, to manage memory automatically. They prevent memory leaks and make your code safer. I'll give a quick example using std unique _ptr below. Example with std unique _ptr, recommended for safety. Key changes asterisk. 1 include memory, includes the header for smart pointers. 2 std unique _ptr node next, instead of a raw node asterisk, we use std unique _ptr node. Unique _ptr ensures that the node pointed to by next is automatically deleted when the unique _ptr goes out of scope. Only one unique _ptr can point to a given object. 3 std unique _ptr node head, the head is also a smart pointer. 4 std make _unique node, new data, this is the preferred way to create unique _ptr objects. It's safer than using new directly. 5 new node dash next equals std move, head, uses std move to transfer ownership of the old head to the new node. This is essential because unique _ptr enforces exclusive ownership. 6 head equals std move, new node, transfers ownership to the head. 7 current equals head.get, uses get, to obtain a raw pointer from the unique _ptr for traversal. You need to be careful when using raw pointers obtained from smart pointers to avoid accidental memory corruption. In summary, asterisk understand the different scenarios for inserting nodes, beginning, end, middle. Asterisk master the pointer manipulation involved in updating the next pointers. Asterisk use smart pointers, like std unique _ptr, whenever possible to prevent memory leaks. Asterisk always consider edge cases, empty list, invalid previous node. Asterisk practice with different data types to solidify your understanding. This detailed explanation should give you a strong foundation for working with linked lists and adding new nodes. Let me know if you have any more questions.